There's an application of just logarithmic equations, logarithmic properties, exponential equations, exponential properties, and it deals with radioactive decay. Radioactive decay is what physicists express the rate of decay in regards to half-life, the time it takes a sample of a substance to decay to half its original mass. So that's what, when we say radioactive decay, and specifically then half-life, is talking about starting with a certain mass. And as that mass decays, it emanates or emits radiation. And say that a half-life is like 1,400 years, and if I start with 100 grams of something, and after 1,400 years, I'm left with 50 grams. It's decayed, it's decreased to that amount. I want to start with kind of talking about the just general rate of growth formula that we know. If we have A of t, we know that it is equal to some initial amount times E raised to some RT, but I'm going to call R in this case just K, some growth rate, okay? Just the way I'm accustomed to using this formula. If we want to know the half-life, what we're saying then is that at an amount at some time is half of what we started with. Well, that's the initial amount. That's what we started with. So in regards to half-life, we're looking at A of t actually being half of the amount you started with. Well, if I kind of work through this and, I got a sub 0, I can divide both sides by a sub 0, and it gives me 1/2 is equal to e to the kt. And then going through and using my logarithm rules, I take the ln of both sides. I get ln of 1/2 is equal to kt. Then what we can figure out is that a growth rate, or in this case a decay rate, is going to equal ln of 1/2 divided by t, where t is your half-life. Okay, so maybe write it this way: half-life, or and. Okay, because we're going to need both these at probably some stage in these questions. If I would have divided both sides by k, I would have had ln of 1/2 divided by k is equal to t, which is your half-life. So this provides us a unique ability to work with radioactive decay questions. I'm going to need this thing here. Okay, and because we're decaying, we're going to find that the growth rate is negative. But K is found this way. If they give me the half-life, I can find that growth rate by this little formula. Or if they give me the half-life and I need to find the rate of decay, I can use this little formula. So it's really nice set of things to look at and use. Now T here, when I use that T right there, that's going to be the T after, like they say, after like 250 years, what's left over. After 100 years, what's left over, and so forth. So we'll go through and do a couple of these examples. First one is the half-life of uranium-232 is 68.9 years. How much of a 100-gram sample is present after 250 years? So we're going to use this. So we're asked basically what amount is left over after 250 years, okay, at that time t. So I've got a sub 0, e to the kt. Well, t in this case is that 250. All right. Now, when we go through and we start filling things in, a of 250 is what we're looking for. My original amount, how much of a 100-gram sample is present? So that's what's left over, 100 grams. That's what, or I guess that's what I start with. They want to know what is left over after we do more. The half-life here is 68.9 years, but we're looking at letting this thing sit for 250 years. So we're going to have less than 50 left over. Okay, and you start doubling, you're probably going to have less than 25 left over. Basically take 250 divided by 68.9 tells you how many half-life iterations you go through, and you start to project the amount that you're going to be left over. I'd probably say maybe in the 8 to 12 range of grams left over, kind of projecting before we really go through the problem. But E is going to be E. Now, I don't know K, and that's coming back up to here. K is the decay rate. Okay, so I'm going to just come to the side and do that work. It's going to be ln of 1/2 divided by my half-life. Well, my half-life is 68.9. That's that easy. There's my K. Okay, so I'm going to type in to my calculator here in a moment, ln of 1/2 divided by 68.9 times then 250 as my exponent. And that should then leave me with an amount at the end. So I got 100. We'll go second ln, so gives me my E. Now I just got to be careful with how I type this. This is all going to be, I think the easiest thing to do is just ln of 0.5, really. Divided by then 68.9. And then I think I can just multiply that by 250. Close that parenthesis off for the exponent. And I should get 8.08. Okay, so the amount after 250 years is 8.085 grams. Which kind of makes sense if you think about, what we started with. We started with 100. After 68.9 years, you'd be down to 50. After another 68.9 years, you'd be down to 25. After another 68.9 years, you'd be down to 12.5. Okay, so I think we've done 68.9 times 4, which would be, or not 4, I guess we did 3. 68.9 times 3 half-life iterations. It got me to 206. So then I need to go, what about 43 more years? So at 3 half-life iterations, I've decreased to 12.5. About 43 more years, or 2/3, I guess, of, or approximately maybe 2/3 of that 4th iteration would make sense that I get down to about 8 grams left over. I got another question here. It says polonium-210 has a half-life of 140 days. Suppose a sample of the substance has a mass of 300 milligrams. Find the mass after 1 year. How long will it take to decay to 200 milligrams? So again, we'll start with A of T is equal to A sub 0 E to the KT. Remembering then that K is equal to ln of 1/2 over my half-life. Okay, because in this case, I'm told the time that I'm interested in, 1 year. So that, I guess there's 2 questions here. Find the mass after 1 year, and then how long will it take to decay to 200 milligrams. Dealing with that first one, find the mass after 1 year. So we start with 300 milligrams. We're going to multiply that by E raised to the K. Now I don't know K. It's this information here, ln of 1/2. Half-life of this thing is 140. Okay. So I'm going to write this as ln of 1/2 over 140 times then T of 1. Now the only thing here that I need to pay attention to is how I deal with this 140, because that's in days and this is in years. Okay, so that needs to kind of be fixed. I guess it'd be the way you want to view this. If we're asked, because this is in days, I probably want to deal with everything in days. So just to make things easier for me in terms of typing this into my calculator, I'm going to take this 1 year and rewrite it as 365. Just make sure as you're doing these, those things are consistent. A lot of times you're going to get your half-life to be in years, and they ask you to check in how many years. So it won't be something I have to address too often. But in this case, because they are different, we gotta adjust. So I get, that value. I'm going to take on my calculator. I'll go 300 second E ln of 0.5 divided by 140, and then times 365. And it gives me 49.23 milligrams. Okay. Which, again, does that make sense? Well, if I double, that's 280. Okay, so 2 half-lives would be 150, and then cut that in half again to be 75. So that would give me 280 days. And then a little bit more of that, okay, even left at 75, go through a couple more days, you can kind of visualize that you'd get down to about 50 milligrams eventually after about 2.5 iterations of half-lives. The next question says, how long will it take to decay to 200 milligrams? So here, this question I think is a little bit more interesting. Now they're giving you that amount there. The amount after time t needs to be 200. We're going to start with 300 again. E, now k, t. Now I know I've got k over here as ln of a half divided by 140, but in this question we're looking for what t is now. Okay, so we're going to take and go 200 over 300. I divide both sides by that constant there of 300, just a little bit easier to do the problem with. And then I've got E. Now K was ln of a half, and you can write this as a decimal if you want to, that's fine. I'm going to leave it as the exact value, so then I've got that. So now I'm going to take the ln of both sides, so I get ln of 200 divided by 300. And now taking the ln of this side would give me ln of 1/2 over 140 times t ln of e. Okay, just putting the ln out here in front. You can take that out in front. Ln of e eventually just becomes 1, so we can actually get rid of that. But now it makes this question multiplied by the reciprocal. I get 140 times ln of 200 300ths over ln of 1/2, and that should give me my t value. Typing that stuff in, then we're going to get, now just think about this, it says the half-life is 140 days, so we know that after 140 days we should get 150 milligrams. Well, we want to get to 200 milligrams, so we didn't get quite a full iteration of 140 days. So maybe this is going to be around 120 days. We'll just see. All right, so 140 natural log. 2/3. You can do that division in your head real quick if you want to, make things easier to type in. And then we're going to divide, I should hit enter first, and then I'll divide that thing by ln of 0.5. Hit enter. You get 81.89. So, my ballpark answer of 120 days was quite a bit off in regards to days, but 81.89 I think kind of makes sense. Yeah, that makes sense. Because we had, started with 300, 140 days, we'll get it to go to 150. So if we're getting in the middle of there, we're getting to 200, not exactly in the middle, but we're getting to 200. Take half of that and you get 70, so 81.9 is not terrible in regards to kind of foreshadowing, projecting what you think you should get as an answer. What I'm doing that for is just to realize that, if I've gotten, if I get 200 back, I know I've done something wrong because my half-life is 140 days, and if I know if I go through 200 days, then I should have less than 150 milligrams, and 200 is obviously not less than that. So just be thoughtful, I guess, of your answers and how they relate back to the way the physics and the chemistry should work.